Essays on the Theory of Numbers by Richard Dedekind. Chapter 1, Continuity and Irrational Numbers. Section 6, Operations with Real Numbers. To reduce any operation with two real numbers, alpha and beta, to operations with rational numbers, it is only necessary from the cuts A1, A2, and B1, B2 produced by the numbers alpha and beta in the system R to define the cut C1, C2, which is to correspond to the result of the operation gamma. I confine myself here to the discussion of the simplest case, that of addition. If C is any rational number, we put it into a class C1, provided there are two numbers, one A1 in A1 and B1 in B1, such that their sum A1 plus B1 is greater than or equal to C. All other rational numbers shall be put into the class C2. This separation of all rational numbers into the two classes C1, C2 evidently forms a cut, since every number C1 in C1 is less than every number C2 in C2. If both alpha and beta are rational, then every number C1 contained in C1 is less than or equal to alpha plus beta, because A1 is less than or equal to alpha and B1 is less than or equal to beta. And therefore, A1 plus B1 is less than or equal to alpha plus beta. Further, if there were contained in C2 a number C2 less than alpha plus beta, hence alpha plus beta equal to C2 plus P, where P is a positive rational number, then we should have C2 equal to the quantity alpha minus 1/2 P plus the quantity beta minus 1/2 P, which contradicts the definition of the number C2, because alpha minus 1/2 P is a number in A1 and beta minus 1/2 P is a number in B1. Consequently, every number C2 contained in C2 is greater than or equal alpha plus beta. Therefore, in this case, the cut C1, C2 is produced by the sum alpha plus beta. Thus, we shall not violate the definition which holds in the arithmetic of rational numbers if in all cases we understand by the sum alpha plus beta of any two real numbers alpha and beta that number gamma by which the cut C1, C2 is produced. Further, if only one of the two numbers alpha and beta is rational, e.g. alpha, it is easy to see that it makes no difference with the sum gamma equal alpha plus beta whether the number alpha is put into the class A1 or into the class A2. Just as addition is defined, so can the other operations of the so-called elementary arithmetic be defined, namely the formation of differences, products, quotients, powers, roots, logarithms, and in this way we arrive at real proofs of the theorems, as, for instance, the square root of 2 times the square root of 3 is equal to the square root of 6, which to the best of my knowledge have never been established before. The excessive length that is to be feared in the definitions of the more complicated operations is partly inherent in the nature of the subject, but can for the most part be avoided. Very useful in this connection is the notion of an interval, i.e. a system A of rational numbers possessing the following characteristic property. If A and A prime are numbers of the system A, then are all rational numbers lying between A and A prime contained in A. The system R of all rational numbers, and also the two classes of any cut are intervals. If there exists a rational number A sub 1, which is less than a rational number A sub 2, which is greater than every number of the interval A, and then A is called a finite interval. There then exist infinitely many numbers in the same condition as A sub 1, and infinitely many in the same condition as A sub 2. The whole domain R breaks up into three parts, A sub 1, A, and A sub 2, and there enter two perfectly definite rational or irrational numbers, A sub 1, A sub 2, which may be called respectively the lower and upper, or the less and greater, limits of the interval. The lower limit a sub 1 is determined by the cut for which the system a sub 1 forms the first class, and the upper a sub 2 by the cut for which the system a2 forms the second class. Of every rational or irrational number a lying between a sub 1 and a sub 2, it may be said that it lies between the interval a. If all numbers of an interval a are also numbers of an interval b, then a is called a portion of b. Still lengthier considerations seem to loom up when we attempt to adapt the numerous theorems of the arithmetic of rational numbers. As, for instance, the theorem, the quantity a plus b times c is equal to a times c plus b times c, to any real numbers. This, however, is not the case. It is easy to see that it all reduces to showing that the arithmetic operations possess a certain continuity. What I mean by this statement may be expressed in the form of a general theorem. If the number lambda is the result of an operation performed on the numbers alpha, beta, gamma, etc., and lambda lies within the interval L, then intervals a, b, c, and so on can be taken within which lie the numbers alpha, beta, gamma, and so on, such that the results of the same operation in which the numbers alpha, beta, gamma, and so on are replaced by arbitrary numbers of the intervals a, b, c, and so on is always a number lying within the interval L. The forbidding clumsiness, however, which marks the statement of such a theorem convinces us that something must be brought in as an aid to expression. This is, in fact, attained in the most satisfactory way by introducing the idea of variable magnitudes, functions, limiting values, and it would be best to base the definitions of even the simplest arithmetic operations upon these ideas, a matter which, however, cannot be carried further here. Essays on the Theory of Numbers. This book was written by Richard Dedekind, translated by Worcester Woodruff Bremen, University of Michigan, published by Open Court Press, 1901. It is being read by Jim Renhold, with programming and illustrations by Jim Renhold, 2019. Thank you for listening.